that's kind of what we always start with. And then we often start with our learning objectives. I'm going to explain those today, but we're actually going to get started with just some of these review topics, actually. So generally, we won't review these review topics, but today I'm just going to go ahead and ease us into this class. And we're just going to cover the idea of nucleophiles and electrophiles. So let me get my work quick here. Get technology. All right, I think that should be working now. All right, so okay. So as I said, we don't generally review the 2301 review topics. We're just going to go ahead and get started today. So we're going to talk about nucleophiles. Yep, didn't stop. Okay. Always technology issues on the first day. So what we're trying to do, I'll give you all a clue here. What we're trying to do is potentially find a way to record and post the lectures after for you to review. So we're just testing that out today. I'll give you more information on Monday if we're able to do it. All right, so nucleophiles and electrophiles is what we're going to be looking at. All right, so whenever we have an electrophile in this class, we're going to identify it and understand where it is on a molecule. So we often can't just say that a molecule is electrophilic. Quite often it has an electrophilic position on that molecule, and very often it has a nucleophilic position. And actually, quite often it has multiple electrophilic and nucleophilic positions. So it's quite important to not just label a molecule an electrophile. An electrophile literally means electron lover. So this is something that is electron deficient, okay? This is a compound that, frankly, it just wants more electrons. Right? Something is pulling electron density away from it, for example, or maybe it has a charge on it. This is something that just wants more electrons. All right, to get us into this, we're actually going to go ahead and take a look at a molecule on CHEM, and you're going to identify where the electrophilic position is, all right? So if you go to CHEM and you go on your Canvas app, we're going to have a couple CHEM questions today, so feel free to leave your phones out. All right, we're going to go to assignments. And we are lecture 2 for CHEM. And we're going to take a look at this first question, which is going to help you refresh exactly what the electrophilic position is on this particular molecule. So this is a ketone, all right? And so you're going to kind of tap the position that you think is the electrophilic position, and we'll get a heat map. So things for you to consider is we have 2 methyl groups. Those are potentially a position that you could think of. Those are equivalent. We have the carbon at the base of the carbonyl. That's potentially something you consider. But we also have our oxygen as well. We don't just have to consider electrophilic and nucleophilic molecules just as carbon. They can be what is called a heteroatom, which is an atom that's not carbon. All right, so where's the electrophilic position on this? All right, so not the carbons. I think that's really great that people were not looking at that position, because that is correct. Those carbons on those methyl groups are not electrophilic at all. In fact, we'll learn later on in this class that those can actually serve as nucleophilic positions. So we kind of have mixed answers between our carbon at the base of our carbonyl and our oxygen. And those are actually, those 2 positions are what we're going to be talking about today. All right, so it looks like everyone seems to have answered. A quick reminder for you that you don't need to worry about getting this right or wrong. You just have to participate to get those attendance points. All right, so we established that it's not these methyl groups that don't have anything attached to them. Instead, it's somewhere else on this carbonyl, all right? So this is a functional group is called a ketone, which is an oxygen double bonded to a carbon with 2 carbon substituents bound to that. Okay, so we need to start, how do we figure out if this is where the electrophilic position is? If this is something that was quite confusing to you, one thing that I always encourage people to do is draw on lone pairs of electrons. That helps us to understand where some of the electron density is. So if we have an electron lover, we might not have something that has a lot of electron density on it. The other thing I would like you to consider whenever you're thinking, is this a nucleophile or an electrophile, which is going to be so key to mechanisms in this class, is what is the charge is? Where is the electron density being pulled, all right? And so we can draw a positive at the base of this arrow, and we can see electron density is being pulled away from that particular carbon. Well, why is that? Well, when we take a look at the periodic table, as I said, we're going to refer to a lot. We can see element number 6 is carbon. All right, and then we see element number 8 is oxygen. And when we think to our periodic trends from general chemistry, we see that oxygen is very electronegative. So it's pulling away electron density away from our carbonyl carbon at this particular position here because it's very electronegative. And so what that does is we have a partial positive charge on that carbon because we pulled electron density away. All right, this is not a full positive charge. We're not drawing this as a carbocation. We're drawing this as a partial positive. All right, the same thing goes, then we can assign the partial negative charge to the oxygen. All right, and the key takeaway here is that oxygen is very electronegative. And so that means the electron density is pulled towards it. All right, so it's pulled toward the oxygen, which leaves the carbon electron deficient. All right, so it's pulled away from carbon. We call this, the carbon is electron deficient. Right? When something is deficient of something, it probably wants more of it back. So now that's how we've been able to identify that our carbon is going to be our electrophile, our electron lover, because it's lacking electron density. It wants more back to it. All right? So we can think about lots of every single organic functional group as part of, the periodic trends that we know. We can think about where the electron density lies on each individual atom. And this is going to help us throughout the entire class, all right? So whenever you see a functional group, this is what I want you to think about. Okay, so if we have an electrophile, we likely need to start thinking about what is the nucleophilic position, because actually this particular molecule can react as both an electrophile as well as a nucleophile. All right, so nucleophiles we're going to identify as something that has a lot of electron density and is capable of giving it up. All right, so we're going to define it sort of loosely as something that can give up electrons. And so you might say to yourself, well, that oxygen there has a couple of lone pairs on it. All right, from our oxygen, lone pairs. Why does it have a lone pairs? Well, again, we can take a look at our Lewis dot structures from our periodic trends. We see that we have carbon likes to have 4 bonds to it, nitrogen likes to have 3 bonds to it and 1 lone pair of electrons. Oxygen likes to have 2 bonds to it and 2 lone pairs of electrons. Fluorine right next door likes to have 1 bond and 3 lone pairs of electrons, right? This is our octet rule that we learned in Gen Chem. Okay, so that's why we have 2 lone pairs of electrons in our oxygen. We have quite a bit of electron density. You'll also recall what we had drawn before is that even more electron density is being drawn towards our oxygen because it's pulled electron density away from that carbon. So not only does it have lone pairs, it also has a lot of electron density that it's stolen from that carbon. And so this is why it's capable of giving up electrons. Right, so one thing in ketones, we often label this oxygen as the 1 position and the carbon as the 2 position, all right? We have lots of different naming conventions that will come up a lot, right? So we can say that the oxygen or 1 position is the nucleophilic position. All right. And the reason is we have that lone pair, 2 lone pairs of electrons. Are on our oxygen. And we have electron density pulled away from our carbon. That was indicated by our partial charges. All right, so this is really going to be super key to how we think about every single molecule in this class, all right? There are molecules that you learned last semester, like the Diels-Alder reaction, that are pi components, and those are a little bit more how we think about them, a little less like nucleophiles and electrophiles, but the majority of this class, if not all of it, will deal with these sort of entities as discrete nucleophiles or electrophiles. All right, so that's what we're going to do. We're going to do an in-depth study of what is called philicity. Right? What does this love? Nucleophilic, electrophilic. So in-depth study of philicity of each functional group. All right, and the reason why we're going to do this is this informs how something reacts. All right, so that's what we do. So as an organic chemist myself, I take a look at a molecule and I haven't memorized it. I see molecules with 10 functional groups in them and I haven't memorized it. I just take a look at the molecule. I think about the periodic trends that I know and I think about how that molecule could potentially react. All right, so how are we going to understand reactivity? We said electrophilicity and nucleophilicity are kind of be our guiding principles. So we can make a list, though, how we will study reactivity. Right, so electrophilicity, nucleophilicity. All right, we also talked about already electronegativity. These are all sort of interrelated, right? So those are the 2 things that we've talked about. And throughout this class, we're also very much related to nucleophilicity and electrophilicity. We're going to think about acidity and basicity. You know, what is being deprotonated, what is doing the deprotonation, and this is quite often very much linked to things like nucleophilicity and electrophilicity. As Libby mentioned on day 1, we're going to think about a lot of reactivity in terms of resonance. You can't get away from that. It really helps us to understand how stable a molecule is. If something's very stable, it's less reactive. We're also going to talk a lot today about aromaticity. All right, so this sort of relates to our 2301 review topics because these are the most important things that we're going to consider throughout this entire class. So over the next 16 or 18 weeks or however long this class is, we're going to study molecules and we're going to take a look at these particular factors. All right, so as I said before, we don't often do the 2301 review topics. We're starting slow today so that everyone can understand where we're coming from in this class. If these words are pretty unfamiliar to you, You know, think about going to OLS and coming to office hours and studying a little bit of these topics in the lecture. All right, as we mentioned on day one, our entire class is centered around learning objectives. All right, and that word may be familiar to you. You may have never heard it before. Both of those scenarios are fine. What is a learning objective? All right, this is a statement that is brief. But specific. And it's a brief and specific statement of what you should be able to do the material when we complete the lecture. All right, so at the end of the day, we're gonna have some learning objectives and we're really gonna get into these more on Monday. We'll have one practice one today, but this is what we want, all right? So our exams will have everything based on the learning objectives. We're gonna ask you something quite specific that has been covered in lecture. And on the practice exams, you can look at the answer key, and the answer key is linked to the specific learning objective that that question is asking. So this sort of is us showing our receipts about this is how we actually write exams on this. So when you get those practice exams, you'll be able to do that. All right, so how many of you have seen the 4 Ps before? All right, so this is some language that's been introduced. So we started it, Professor Lamb and I started this in our class, and then we thought it was quite effective. So some people in 2302 have been using the 4 Ps as learning objectives, but not everyone is familiar with these. So we will go ahead and go over what the 4 Ps are. And whether you know these or not, you know these, all right? So the first of the 4 Ps is to propose starting materials and reagents. All right, these are those pesky things that you have to put over the top of the arrow that you see on exams all the time. You have something and you go to something else. How did you get there? Those are the reagents. So that's what the first P. The next P you will remember all the time on exams, which is predict the products, where you're given the starting material as well as the reagents, and then we say, what did this make, right? And so we first categorize these particular ones as these are the 2 Ps, all right? So if we say the 2 Ps, we're talking about these first 2 ones. And when we talk about the 4 Ps, we're talking about mechanism questions, those pesky arrows that you have to push around, all right? And we start that with picking out the electrophile and the nucleophile. All right, that's just what we did today. We did an in-depth analysis of what is electrophilic, what is nucleophilic. And then you need to get going on your provide the arrow pushing mechanism. All right, these are the 4 Ps. And for most reactions, the first one we're going to learn is something called electrophilic aromatic substitution. And we're going to first learn on a nitro group. So your learning objective is going to be the 4 Ps of the electrophilic aromatic substitution of benzene to form nitrobenzene, right? Very discrete and specific or concrete and specific language there, what we want you to do. And we want you to propose the starting materials, predict the products, pick out the electrophile and nucleophile, and then get going on providing the arrow pushing mechanism. All right, so this is going to happen over and over again. I'm not going to write out these learning objectives, each of the 4 Ps every single time. All right, so that is going to be how we're going to go ahead and handle these. All right, so now let's get into some chemistry. All right, Now we sort of laid the foundation of how we're thinking about things and how this class is going to run. The first things I went through, announcements, learning objectives, and review topics generally take 3 minutes in the beginning, but we're taking some time to get everyone up to speed. But now we're going to go into the chemistry. All right. So we're going to learn about arenes, and you've already learned about these. These are also called aryl rings. We have a number of different names for them. Benzenes. All right. We abbreviate this AR for aryl, and that means that these are aromatic. All right. So you often see benzene, but we're going to find ways to make a lot of benzenes. All right. So for some reason, benzene is abbreviated as phenyl, but when we're dealing with general aryl groups, we're going to say AR. All right, so benzene, just simple benzene on itself, looks like this. All right, so this is benzene. Okay, and we abbreviate that as pH for phenyl. All right, so what did we do at the beginning of the class? We assessed whether something was an electrophile or something was a nucleophile, all right? So that's gonna be our second chime-in question for the day. What is benzene? Is this an electrophile? Is this a nucleophile? So let's go ahead, and again, it's gonna be in lecture 2 assignments, and you're gonna tell me what you think. Is this an electrophile? Is it a nucleophile? Could it be both? Is it neither? We know that aromatic compounds are quite stable. And then sometimes we include a question that is for the honest people in the group that are like, I'm not sure, and that's totally fine. That's why you're in class. You're in class to learn, not because you know everything. All right, let's see what people think here. Okay. All right, so we have a lot of could be both camps. We have team electrophile, team nucleophile, team neither. Maybe those folks are thinking about the fact that aromatic compounds are quite stable, so they're not often reactive. All right, great. So it looks like we've had everyone respond here. I'll give it another couple of seconds. As a reminder, if you're in the class and your device isn't working, just come up to one of the TAs or myself afterwards, and we can go ahead and get you recorded for being here. All right, so I'm going to close that question. All right, so let's think about team nucleophile first. What were those folks likely thinking? Well, they were likely thinking that there's a lot of electron density. All right. There's quite a bit of electron density there. We have a lot of pi bonds. We have a lot of electrons. We have this electron cloud in our aromatic ring. We have 6 extra electrons, right, with those double bonds. So yeah, benzene can be nucleophilic. All right, because there's a lot of electron density. All right, so what do we think about the potential for these to also be electrophilic? And this camp is people thinking about whether they were both electrophilic and nucleophilic or not. So I'm going to draw an additional group on here because we're not just talking about benzene, we're talking about arene rings, right? And this is a molecule, this nitrobenzene, that you're going to see a lot, okay? So we have an electron withdrawing group. All right. And so we're pulling electron density away. We often abbreviate electron withdrawing group as EWG. So we have an electron withdrawing group on here, and this is pulling electron density away. And it's pulling it towards those highly electronegative groups, and it's pulling it away from the arene. And so when this happens, this is an electrophilic molecule. And that's what this chapter is. We're learning about electrophiles and nucleophiles through the lens of benzene and arine derivatives being both. Okay, so how do you figure out what we're doing in which particular part of the chapter, right? So in order to determine the philicity, we need to look at one. So in order to determine philicity, we need to first look at other reagents. See if we can tell if those are electrophiles and nucleophiles. We see pairs. We see an electrophile reacting with a nucleophile. We don't see two electrophiles reacting together. We don't see two nucleophiles. So we can kind of pick up clues from the other reagents that can help us. The other thing that we can look at is the electronics of the benzene or the arine. So in this particular scenario, we would look and we would say, well, we have a lot of electron density when our unsubstituted benzene, so that's probably a nucleophile. We would look and see electron withdrawing groups on our nitrobenzene. We say that's probably an electrophile, right? So we have to take sort of a holistic view of everything going on in the reaction to understand what is happening. Just like with the ketone that we saw before, what we saw with that ketone is it could react as either an electrophile or nucleophile, right? We had two positions that had opposite philicity. Same thing with benzene. So we need to take into account everything else that's going on in the reaction to be able to determine fully that third P of picking out what is the electrophile and nucleophile in the reaction. All right, so let's get into benzene acting as a nucleophile. And this is called electrophilic, aromatic substitution. We will also be abbreviating this a lot, EAS. So that's a lot to write out. Later on in the chapter, we're going to learn about nucleophilic aromatic substitution. So this is because we know that arenes can react as both. Okay, electrophilic aromatic substitution. An electrophile is substituting your aromatic ring, which means that your aromatic ring is the nucleophile. All right, so we'll get started at identifying our starting materials and our reagents. All right, I'm going to suggestively draw in one CH bond. Of course, there's 6 CH bonds on this molecule. I'm going to label this our nucleophile. All right, and then the other reagents, we're going to get into halogenation, nitration, sulfonation, acylation, alkylation, but we're going to group all those into having an electrophile. We'll define what all of these are next week. So this is our electrophile. Electrophilic portion of the molecule. And that is going to be bound to a leaving group. You'll recall lots of leaving groups. We have to have some electron density, attack our electrophile, and something has to leave. All right? So this is our electrophile overall in the reaction, and those are the individual pieces of it. Okay, so we're going to have our reaction arrow. So now that we're going to go and we're going to predict our products, what our products are going to be is our benzene that is now bound to our electrophile. And that proton that I suggestively drew is now affiliated with that leaving group. Right, so some instructors don't show you what the byproducts of the reaction are. I think these are really important to understand where everything went and helped us to figure out the mechanism of the reaction. So I'm going to always try to draw in the byproducts. What we want is our product, that's our benzene derivative. We don't really care about this H leaving group situation, but I'm going to draw it in because that's going to oftentimes come into play with the mechanism. All right, so this is the only time I'm going to draw out P1. So this is providing our starting materials. And reagents. So in this scenario, this is our electron-rich arene. Right, that's labeled as our nucleophile there. Or it could be neutral as well. Actually, I'm going to add that caveat in, electron-rich or neutral arene. All right, now we also have our strong electrophile with a good leaving group. All right, P2 in this scenario is predict the products. On an exam, if we said P2, what you would draw is going to be our arrow ring with electrophile substituted for H. Right, tons of exam problems come from just these two P's, right? We have a row of things that have boxes for the products, and that's P2. We have a list of reactions with nothing over the arrow, and that's the reagents. Or we'll have a list of reactions with no starting material, but we'll have the products, and you'll be able to predict that, right? This is quite often what we do. And then, of course, P3 we've done is pick out the electrophile and nucleophile. We've done that above, right? And the reason why it's really important to pick out our electrophile and our nucleophile is for our arrow pushing mechanisms, because that's P4. I'll let you all get a second to catch up on writing. The dreaded arrow pushing question.
Just a quick question. So if the H was bonded with like a wedge on the benzene, would the electrophile invert the stereochemistry?
Yeah, that's a super great question. I like that you're thinking about the mechanism of something like an SN2 reaction, right? I think that's awesome. So in this particular mechanism, due to the hybridization of the carbon, we don't have wedges or dashes, but that's a great consideration when you're thinking about mechanism, whether you get inversion of the stereocenter. So yeah, excellent question. In this case, we won't really have to run into that because of the hybridization, but I like that you're thinking mechanistically. All right, so P4, arrow pushing mechanism. Right. So as I said before, I'm not going to write out all of these categories from now on, but on the first day of class, I want everyone to be caught up to speed. Okay, so we're going to have our benzene ring here. I'm suggestively drawing in that CH. Doesn't matter which CH it is. I'm going to draw our electrophile and our leaving group, and I'm going to draw the generic mechanism. Right, and as we go along in this class, electrophile and leaving group are all going to behave a little bit differently. And so the generic mechanism and the patterns that Professor Lamb talked about on the first day still hold, but it's going to look a little bit different depending on what we're substituting with. All right, so what we're going to do is we're going to take our arrow and we're going to start from this double bond. That's where electron density is. We're going to attack our electrophile, meaning the arrow is going to point to our electrophile. Okay, this is our first arrow in this mechanism. And I'm going to draw out, again, for just today, what each of these arrows mean. And then from then on, we're just going to draw the arrows themselves. Okay, but when drawing a mechanism, we have to start from electron density. Right, so this is our nucleophile. I oftentimes see people pushing an arrow from H plus that has no lone pairs of electrons or electron density. So electron density generally comes from double bonds. So in this case, that's where we started from. And it comes oftentimes from lone pairs of electrons. So we often abbreviate electrons as E minus. All right. So that's generally where we need to start our arrows. Electron density. Electron density is flowing from a lot of electron density to a place where it's sort of like a vacuum. It's pulling it that way. It needs electrons, so it's pulling that way, right? So it's coming from the nucleophile going towards an electrophile. Not the other way around, okay? And we get a new bond. Or we form a lone pair of electrons. So in this case, we're forming a new bond. Okay? So we're forming a bond from that lone pair or from that electron density and that double bond going towards our electrophile. And then this is similar to an SN2 mechanism where we're going to break the bond between our electrophile and our leaving group, and we're going to place a lone pair of electrons onto that leaving group. All right, so the second arrow is electrons from the bond. Remember, a bond is just two electrons being shared, okay? So electrons from the bond of E leaving group must leave with the leaving group. Right, in this case, a bond is broken. If it's a double bond is broken. In this case, we're breaking a single bond, so it's always breaking that. Right, and this is often becomes a negative charge. And this is often a lone pair of electrons. All right, so it's a lot of words, right? But I want to write out what mechanisms are from day one. So we can just, based on our chemical intuition and understanding of what these arrows fundamentally mean, we can go in and draw the intermediate in this reaction. All right, we've done nothing with this H here, but we have broken a double bond. What we've done is we've taken those electrons and those are now bound to our electrophile, right? But the double bond was shared between two atoms. Only one of those atoms got in our, actually for clarity, sorry, I'm gonna do this a different way. Okay, so for clarity, I'm gonna draw the electrophile bound here. It doesn't matter, there's a CH bond on everything, but yes, I think that would be easier to understand. Okay, so we used to only have one CH bond here. That is, okay, so we have our CH bond, and now we have this other carbon that's below the CH bond, this one here, that's now missing electrons. We pulled the double bond away from it. So that means we need to put a carbocation at that position. Right, so that's why I sort of suggestively drew that particular CH, all right? So our carbocation is there. Right, so we went from a double bond to a single bond, and at the top we have 4 bonds to carbon. Great, it's very happy. On the bottom, we have, I can even draw in, let me draw in another color, this other CH bond here that we see here, and we see there's only 3 bonds to that carbon, so that's why it has a carbocation. Right, at that position. All right. And now we need to consider what we said in step 2. We have our leaving group that now has a lone pair of electrons on it because it took that electron density with it and it has a negative charge. All right, so that's the first part of our general mechanism. So let's go ahead and keep going, all right? So I'm gonna just redraw this at the top of this slide so you have the full mechanism. All right, we have our CH bond here, draw this one in. We have our electrophile and our leaving group. Have our benzene ring. Now, after those first two arrows, that has a positive charge, carbocation, carbon bound to our electrophile. You see that CH bond there is electron deficient. All right, and so the arrows came from the benzene ring to the electrophile to the leaving group. All right, so we have that leaving group that is negatively charged with that lone pair of electrons on it, right? And so we know how to quench carbocation reactions, right? What we can do is we can take a third arrow, and that lone pair where the arrow is going to originate from can go ahead and deprotonate that CH bond. So that's arrow number 3. And as soon as it deprotonates that CH bond, we now have those 2 electrons in that CH bond that we can go ahead and give back to our benzene ring so that we are quenching that carbocation. Right? And that's why at the end of the day, what we get is this substitution where that blue CH is gone because it's been deprotonated. We no longer have a carbocation near the teal CH. And we have our leaving group that now has a proton with it. That leaving group has acted as a base. All right, so let's talk about arrow number 3 is a deprotonation. Of that CH bond to quench our carbocation. All right, and arrow number 4 is the electron density from that CH bond. We form our double bond. And this is going to be the pattern that you see over and over and over again. The identity of E leaving group is going to change, so this mechanism is always going to be roughly the same. Electron density attacks from our benzene ring to our electrophile. Leaving group leaves. We quench that carbocation through deprotonation. We're going to see this over and over and over and over again. All right? So the one learning objective that I want to touch on for today is our learning objective, and I'm always going to label these. It makes from now on, they're always in order. It's not 13A today, it's 13D, but I swear from then on it is. And this is going to be recall how resonance stabilizes. In this case, it's stabilizing the carbocation. All right, so on our mechanism, we had this intermediate that had a double bond here. It had our H here, our electrophile. We know that carbocations are not stable, happy. Oh, question. Oh, yes. Good? Okay, great. Yeah, please, if I'm ever going too fast and you didn't have time to write something down, I'm happy to go back. Okay, so we have this carbocation. We know that carbocations are not very stable, right? They're unhappy, they're electron deficient, they're highly reactive species. All right, and we had our leaving group that is sort of acting as our counterion, right, for this. So we can think about stabilizing this carbocation through resonance. Recall that this is a resonance arrow. All right. So we can start to think about how we can stabilize that carbocation through resonance. We can take this neighboring double bond and move it over to quench our carbocation. All right. It's in conjugation. This is an allowed move in organic chemistry. And so what that does is it leaves the carbocation on this different carbon, all right? So what this is doing is basically it's sharing that load of this really unfavorable species, all right? It's putting it on one carbon, moving it over so they can kind of share that load. We can do this even more. We can continue to share the load over a different carbon, taking that double bond on top. We can move it to quench that carbocation this time, right? And so then we'll go ahead and have a carbocation at a different position, all right? All right, we haven't done, in this case, we're not doing any deprotonation or anything like that. We're just stabilizing that carbocation. It's very unfavorable. These atoms are sharing the load of having this unfavorable interaction. Notice our leaving group just gets carried throughout. Nothing happens with this yet. It will be used later to deprotonate, but it just sort of follows it around to balance our charges, right? But it's resonance that's doing the stabilization. All right, so resonance is going to come into play over and over and over again, all right? So understanding how resonance stabilizes is something that you're going to want to practice this weekend. All right, so we're going to turn, starting on Monday, we're going to turn this benzene into nitrobenzene, into iodobenzene, into tert-butylbenzene, into acetophenone, but a ketone, and it's all going to go through this mechanism. And that is all that I have for you today.